So I wanted to start this off by speaking about why I'm doing this question itself, because let's look at it. It's a fairly complex looking question, literally and metaphorically. But the reason I'm doing this is because it's a perfect example of a type of question that looks tremendously difficult, um, and might put many students off solving it just because it looks that way. But in reality, if you look at it objectively, it's not too bad. So it's like if you meet a pretty girl and you feel nervous talking to her, but it would be so much easier to talk to her if you would just act normally. Um, it's literally this, like you look at it, you feel nervous, just treat it like any other question and you'll be fine. So let's go for it. So first, we'll consider this expansion as it says in the question, and obviously we have a formula for that because it's a geometric series. So our formula is given by, well, if you remember, a times r to the n minus 1 over r minus 1. And well, we can label well, if we write out the expansion here, we have n equals 0, n minus 1, z to the n is equal to 1 plus z plus z squared plus z cubed to z to the n minus 1, right? We're given that. So filling in that formula, a is the first term, which is 1, and r is our increasing term, our changing term, our ratio is z. So this formula would be given as 1 times z to the n minus 1 over z minus 1, which expanding that into its complex form, because it's z is a complex number, we can write it in exponential form, which is e to the, let's write this out, e to the I theta all to the n minus 1 over e to the I theta minus 1. And obviously with the rule of powers here, it would just be n times I theta, so we can remember that. And what we're going to do is, for a question like this, we, we want either all of it to be complex, all of the fraction to be complex, or none of it to be complex. So let's times it by a conjugate, which is equal to 1, so it doesn't change anything. But we're going to make all of it representative of a complex. And because we've got our half angle in in what we're showing here, so I made a whoopsie there and just lost like a ton of progress because I was a stupid idiot. But yeah, so we're going to times by our half angle here. So I half theta over e to the I half theta, using the Moivre's theorem. Well, we're not going to get to that yet, actually. Let's just expand everything first. E to the I n minus a half theta, we'll put the theta outside, minus e, should be minus that, e to the minus I half theta over e to the half theta minus e to the minus a half theta, and putting that into its modulus argument form, we will be given, let's try and fit this into the space we're given here. You've got your cosine n minus a half plus I sine n minus a half, yep, minus cosine half theta plus I sine a half theta. And that's over, referring back, that's a terribly drawn fraction, Jesus Christ. Referring back to our sine identity there, this is just 2I sine a half theta. And because we're looking for the cosine that is why am I bad at drawing today? I'm horrendous at drawing today. It's asking for cosine n theta, which is the real part. Let's see if I can draw a better segment. There you go. The real part of this sum. We're looking for any part without a complex number, which is typically the cosine, but here it's not going to be the cosine. If we look here, we have a 2i in the denominator and 2 i's here in the numerator, so they'll cancel out, and the cosines will be left with a division factor of iota of I. So those are going to remain complex. So the real part is actually literally just going to be the sine with the i's cancelled out. So let's look at the sine n minus a half plus sine of a half theta all over 2 sine a half theta. And if we look back up here, matches, and we are correct. So there you go. A little bit confusion there today. My brain's fuddled. I haven't done math properly for a few days now. But yeah, I hope that you can understand that. Yeah.